Okay, again, thank you very much. Happy to be back again here in the EC3. My name is Thamer. I'm gonna today present to you our work on prescriptive maintenance of sewer systems based on large language models, and I hope I will not fall during the presentation. So, as a little bit of a topic background, we all know the importance of sewer system as a critical infrastructure for public health, environmental protection, as well as flood prevention in some cases. And when it comes to sewer system, similar to other infrastructures, the reliability of those infrastructure could be compromised due to aging, due to increasing hydraulic loads coming from our ever-growing cities, as well as from climate change. Now, if we take Germany, for example, we have a total of 600,000 kilometers of sewer systems with an average age of 37 years. This gets even worse. So, for example, where I came from in Hamburg, 15% of our sewer system is over 100 years old. So this brings to us or puts in our table the importance of maintaining those sewer systems to ensure a healthy, long-lasting infrastructure. However, when it comes to decision making of sewer systems, we usually have to deal with multidimensional data coming from different resources, from SHM, from reports, from images, and interpreting all of these data and translating them into a stepwise repair procedure is a bit of a challenging task. This is why we thought about introducing a framework. We called it prescriptive maintenance, in which we used a large language model and adapted it to the domain of sewer systems maintenance. Now, as we all know, sewer LLMs, they're pretty good when it comes to self-learn complex relationship and deal with heterogeneous data. They also have the advantage of learning from repair and rehabilitation standards that already exist. So when it comes to our approach, similar to any machine learning approach, you have a phase of data preparation and pre-processing. You also have a phase of fine-tuning or training your large language model. Now, to explain each step, first, we looked into already existing repair and rehabilitation standards. And those in Germany, we have standards coming from the German Institute for Standardization, as well as for the German Association for Water, Wastewater, and Waste. Now, at the end, when we filter these standards and standards parts or standard series, we found 33 standard parts that mentioned or spoke about sewer system maintenance. Now, for the second step, it was about pre-processing these standards. So usually those standards, you find them in the form of a PDF. So you need to translate them into a language that can be understood by machines. So we use the Python pipeline with optic character recognition to translate them into texts. And those, in the standards, there is also tables, which contains critical information as well as figures. So the tables got translated into CSV files and the images into PNG files and got referenced within the text. Now, the next step is how can we extract the knowledge from this? So we thought the best way would be to translate them into Q&A, a Q&A database. And the way we did it is we took those text files, the CSV files, PNG, again using Python. We spoke a bit with our friend in ChatGPT and asked him to create this Q&A database for us. Now, it sounds a bit arbitrary, so we thought maybe we could find a way to constrain the process a little bit. So again, we took all these standards parts, we throw them into Python, again using ChatGPT, and asked ChatGPT to create a summary for these standard parts. And then we use the summary to constrain the other chat or the other conversation with the second ChatGPT. And at the end, we have a total of 9,500 Q&A pairs. Now, this is the distribution from the different standard series. We have the highest number coming from the DBA M143, which was the biggest part that spoke about sewer system maintenance. Now, when it comes to the data, we noticed in the generated So we used a cosine similarity filtering to remove these duplicate data, and we ended up with having almost 9,000 Q&A pairs. Now, again, you have the classical machine learning approach by splitting your data into training, validation, and testing. And then from those testing, we held out 200 Q&As, and I will speak about them again in the validation test. For the next step, it was about selecting a large language model. So we wanted, or the criteria for us for selecting a large language model was we wanted a model that have a parameter scale relatively okay with the hardware we have. We also wanted a large language model that it's open and can be reproduced. So we ended up at the end having two candidates, DeepSeek and Mistral 7b Instruct, and we selected the Mistral 7b Instruct because, indeed, only because of the hardware limitation. Now, when it comes to fine-tuning the model, and here I'm using the word fine-tuning, not training. As we all know, training a large language model is a challenging task and needs a lot of resources. So what we're trying to do is to fine-tune the model. What I mean by fine-tuning is try to align the model with the language, terminology, and context of what you want to use it for. So what we have used for fine-tuning is something called low-rank adaptation. This low-rank adaptation has an advantage of being fast and can be done using the standard hardware, and also returns the general knowledge by this LLM, and also is scalable, and you can translate the knowledge for other application into your domain with minimal overhead. So in the training process, or sorry, fine-tuning, we use the training dataset and validation dataset, of course, to fine-tune the model, and at the end, we check the accuracy of the model using the testing data set until we were satisfied with the accuracy of the model. So we got a mean token accuracy of 91%. So we took this model and considered it done. Now for the validation test, if you remember, I spoke about a held out testing data set, 200 Q&As. Those 200 Q&As, we selected them and we made sure to cover different damage scenarios, different damage locations, as well as different repair severity levels. Now, we throw the questions to both models, the Mistral model, the baseline one, without fine-tuning, as well as the adapted one, after fine-tuning. And we design a scoring rubric that considered, for example, structural clarity of the response, conformity with the standards. We also introduced a hallucination penalty. And then we saw or tried to see how each model performed. So this is the performance of the both models. We have the Mistral 7b, the baseline model scored 4.8 on our scoring rubric, and we had the adapted one had a higher score that scored 7.6 out of 10. Now, this is one of the questions we asked both models, and this is the answer generated by the baseline model as well as the answer generated by the adapted model. What we have noticed is the baseline model, the answers are still fragment, even though sometimes it was occasionally mentioning a standard or a source, but this was not the case in the adapted model. So it was more structured and more clear and more domain specific. To not take too much time, to summarize what I have just said, so we all know the importance of sewer system and maintaining our sewer systems to ensure a long-lasting, healthy, and functional infrastructure. When it comes to traditional decision-making, they often fall short to deal with heterogeneous and multidimensional inspection data and translate those data into an actionable maintenance strategies. And this is why we were working on the framework called RxM, Prescriptive maintenance, using large language models, in which we used this retrained LLM and adapted it to the domain of sewer systems. And for our future work, we would like to improve a little bit the uncertainty handling by our models, as well as try to validate it further using real-world sewer system inspection data. Thank you very much.